Hi everyone. In this video, we'll continue the discussion about improper integrals. So far, we've only looked at examples containing a single improper feature that happens to be at an endpoint. But what should we do if it's in the middle of our interval, or even if there are multiple improper features? For that, we need to remind ourselves of an important fact about integrals. When we think of a definite integral from a to b, we know that this is interpreted as the net directed area under the curve. Now, let's say we chose some point that I'll call C within this interval. Notice that we could use that point to divide our area into two subregions. The area to the left of that point could be seen as the integral from a to c, and the area to the right of that point could be seen as the integral from c to b. And by adding those together, we would find the total area, or I guess directed area, of our region. And this shows the integral we started with, which is from a to b, is equivalent to the integral from a to c plus the integral from c to b. If we were ever in a situation where we had multiple improper features, we could use this fact to split up our integral so that each term only has one improper feature. Let's give it a try. We can see right away that there are two improper features here. There aren't any discontinuities, but both of the endpoints are infinite. So instead of integrating from minus infinity to infinity, we could split this up and instead take the integral from minus infinity to 0, then add the integral from 0 to infinity. Here I chose to split up my integral at x equals 0, mainly because 0 tends to be an easy number to work with, but technically it would be possible to use whatever value you wanted, so it certainly didn't have to be 0. Now let's label these integrals as 1 and 2. The problem now boils down to calculating both of these and then adding the results together. So let's start with the integral that I just labeled as 1. We can't really evaluate from negative infinity to 0, so instead we evaluate from t to 0. Then we let t approach negative infinity by applying this limit. To calculate this integral, we need an antiderivative, but in this case that's easy because you can refer to your formula sheet to see this as arctan x. Next, we need to plug in our integration limits, resulting in arctan of 0 minus arctan of t. Now, since tan of 0 is 0, we know arctan of 0 is also 0. You can convince yourself of this using the unit circle if necessary. Next, we let t approach infinity and see what happens. Now, how do we interpret this expression shown as arctan of negative infinity? For that, we need to be aware of the behavior of the arctan function. We know if we take the graph of tan x and then reflect it, we get the graph of arctan x. And that's due to the fact that these are inverse functions, so their graphs are reflections of each other on the line y equals x. Now, we know the graph of tan x has vertical asymptotes at pi over 2 and negative pi over 2, and due to the switching of x and y, these will become horizontal asymptotes for arctan. Now looking at this graph, we can see that as x goes to negative infinity, the y value is approaching negative pi over 2. Then, by canceling the double negatives, we get a result of pi over 2, which concludes the calculation of this part. Next, we need to calculate the integral labeled as 2. We can reuse the antiderivative we found before, since this is the same function after all, but the limits are different. Now, we can't evaluate this from 0 to infinity, so instead we evaluate it from 0 to t, while ensuring that t approaches infinity. Then we plug in the upper and lower limits to get arctan of t minus arctan of 0. Just like before, we know arctan of 0 is 0. Now let's see what happens when t goes to infinity. To understand this result, we once again need to understand the behavior of the arctan function. So let's refer back to this graph. We can see that as the input x goes to infinity, the output y is approaching positive pi over 2. So the expression shown as arctan infinity can be interpreted as such. Now that we've found the values of the integrals labeled 1 and 2, we can just add them together to form our final answer, which in this case is pi. Since we got a finite value, the terminology we discussed in the previous video would suggest that this was a convergent integral. Notice that since the integrals labeled as 1 and 2 were both convergent, that actually caused our original integral to be convergent, because after all, the sum of two finite values must still be finite. Similarly though, if we had found that either of the integrals labeled as 1 or 2 were divergent, then we would say that the original integral was also divergent. What that means in practice is that if you were to calculate the integral labeled 1 and find that it diverges, then you don't even need to bother calculating the integral labeled as 2. Your conclusion would just be that the original integral diverges, and that would be the correct answer to the question. Just to be clear, when you're asked to calculate an improper integral, that means you want to either find its value or explain why it diverges. Let's give this a try. First of all, why is this integral improper? The reason is because there's a discontinuity when the denominator is 0. But which value of x is that? Well, to figure that out, we just do a bit of basic algebra. By applying the natural log to both sides, we can find that discontinuity occurs at x equals ln of 2. And you can check that ln of 2 is about 0.69. That means integrating from -2 to 2 would require us to jump over this discontinuity. So instead of going from -2 all the way to 2, we instead need to go from -2 up to the discontinuity. Then we go from the discontinuity up to 2 and add these results together. Each of these terms now contain only a single improper feature that occurs at an endpoint, so we're prepared to calculate these in the usual way. But which one should we calculate first? My suggestion is to pick the one that looks most likely to diverge, because if either one of these is found to diverge, then we don't need to bother with calculating the other. There's no way to know for sure without doing the math, but when we look at the graph of this function, it looks a bit like the green area is larger than the blue area, which suggests divergence of the second integral might be more likely. So let's start with that one. But be aware that if you hadn't made these considerations and let's say instead you started with the first one, that's also fine. You would end up with the same answer at the end of the day. So not really a big deal to make this prediction. It might just save you some work, possibly. Now to actually calculate this integral, we can notice the function we've been given has the form of f prime over f. So we know the antiderivative will be the ln of the denominator with an absolute value. Now, we can't evaluate this from ln of 2 to 2 due to the discontinuity, so we instead evaluate it from t to 2. Then we take the limit as t approaches ln of 2 from the right. It's from the right because when we go from ln of 2 up to 2, we only need to consider values that are larger than ln of 2. Now remember that whenever we see an improper feature, we should always be considering which side to approach from in order to get the correct answer. Next, we evaluate this by plugging in our upper value, which is 2, and then plugging in our lower value, which is t. Now we need to apply our limit to these results. So we let t approach ln of 2 from the right and see what happens. Notice a cancellation law can be applied here, leaving us with these results. And now in my second term, I see that 2 is being subtracted from a number slightly larger than 2, which would result in a number slightly larger than 0. You can refer to the familiar graph of ln of x to check that when we plug in x values which approach 0 from the positive side, the y values go down to -infinity. The first term here is just a number which won't stop this from going to infinity. So with that, we are done calculating the integral which was labeled as 2. Now, going back to the question we were actually asked, we found this second integral is divergent since it evaluated to positive infinity. And because of that, we conclude that our original integral also diverges. We don't even need to check the value of the first term to make this conclusion. You might wonder if it was really necessary to treat this as an improper integral, since if we hadn't noticed the discontinuity, it'd be pretty tempting to just find an antiderivative and evaluate the same way that we normally would. I encourage you to pause and try that. If you don't treat this as an improper integral, you will come up with a different conclusion, and it would be the wrong conclusion. The reason it's wrong is because the fundamental theorem of calculus only applies to continuous functions. So in the future, watch out for discontinuities, and if you see one, be prepared to use the methods from this video to deal with it properly. That's all I have for now, so I'll wrap things up here and see you next time.